Hello, let us continue looking at the reactions of ketones and aldehydes, and we are up to the reactions where oxygen is going to be the nucleophile. Let me remind you that in video number 02D20, we looked at the Wittig reaction, and we could think of that also as a carbon nucleophile reaction, and we also saw some other carbon nucleophiles such as cyanide and the alkenyl anion. In this video, Hydrate Formation, Hemiacetal, and Acetal Formation, all of those involved oxygen nucleophiles. And we are up to Rxn D, Hydrate Formation. When you mix any ketone or aldehyde in water, you're going to hydrate that molecule, but not to a great extent. Let's take, for instance, acetone plus water. Most of the resulting molecules will be the starting material, and then we'll have a small percentage of what's called the hydrate. We're literally adding water. As you can see, we added an oxygen and two hydrogens to this molecule here. It occurs via the attack of the carbonyl carbon via water. This is particularly called a gem diol. Gem meaning Gemini. The two hydroxyl groups are coming from the same carbon, or are attached to the same carbon. I'm not going to go through the mechanism of the hydrate formation. It's a pretty simple reaction. We are going to go look at the mechanisms, though, for hemiacetal and acetal formations, which are, I think, more important. Just one more note about the equilibrium. It favors the left side because carbon-oxygen double bonds are fairly strong and stable. And in a reaction, you typically do favor the side that gives you the more stable products. Now, before we look at hemiacetal and acetal formation, I do want to foreshadow what we're going to see in Unit 3. Unit 3, we're going to talk about carbohydrates. And the reactions that we are going to learn about in this video are going to be very important to remember when we do get to carbohydrates. Because the hemiacetal reaction, that actually is a reaction that acyclic glucose undergoes to make cyclic glucose. Acyclic glucose. Glucose is a monosaccharide, or you could even think of it as just a plain carbohydrate molecule. And it will cyclize, it will form a ring doing a hemiacetal reaction. The acetal reaction we are going to learn today, that is used to hook up to glucose molecules or to any two monosaccharides to make a disaccharide. So I understand that these terms are a little bit unfamiliar. Don't worry about it. We'll define all these terms in Unit 3. I just want to give you a target, a reason why we are learning now hemiacetal and acetal formations, because we're going to apply these simple organic chemistry reactions to biomolecules. And the example that I want to show is glucose plus galactose to make the disaccharide lactose. I do have some websites queued up. Let me see if I could find those. Here. This process to go from acyclic glucose to cyclic glucose occurs via a hemiacetal formation reaction that we're going to look at in just a bit. And then check out this ring. If we have that ring plus a ring of, it's called galactose, when you hook them up together to make a disaccharide, that is via a acetal formation. Okay. Well, why don't we go ahead and look at hemiacetal and acetal formations. This is going to be reaction E, hemiacetal formation. Hemiacetal is a molecule that has a carbon attached to a hydroxyl group and what's called an alkoxy group. The other two bonds could be to another carbon or to hydrogen. I'm not worried about that. This is a hemiacetal. Hemi meaning half, so we could also think of this as a half acetal, but we'll see what an acetal is in just a bit. What you want to look for is there a carbon on your molecule that is attached to a hydroxyl group and an alkoxy group? If you do, then you have a hemiacetal. We are in the ketone and aldehyde unit. How do we convert those molecules into a hemiacetal? We can take, for instance, this aldehyde, and we're going to supply an alcohol. The alcohol I'm going to supply is methanol. It could be any alcohol. But to make it the hemiacetal, okay, we only want to add one of the alcohol groups. So we're going to say that this is only one equivalent. This is probably the first time in these videos where I talked about equivalency, and when I'm specifically telling you that this is not in excess. It is one equivalent, or one molecule of methanol per one molecule of aldehyde. This is a acetalized process, and to draw the product, let's put a dot on the carbonyl carbon, and that's the carbon that is of interest, the one that has the hydroxyl group and the alkoxy group. So here's your dot, here's your H. We have a hydroxyl group, and what is the alkoxy group? Well, the R is going to match the R group of the alcohol, CH3. We do remove this hydrogen eventually, right? You can think of this as a oxygen neutral nucleophile, and typically when you have a neutral nucleophile attack, you're going to remove a hydrogen to get it back to neutral. Okay. If the hydrogen was still attached, that oxygen would be positive. This is a hemiacetal. Now, we could do the same thing with a ketone. And let's take, for instance, a cyclic ketone. Let's use one equivalent of another alcohol, and I'll use 2-propanol. Can I switch up the acid? Let me switch up the acid and make it hydrochloric acid. Okay. All right. So do the tricks that we did up here. Put a dot. Draw your carbon skeleton. Here's your dot. That oxygen actually is the oxygen that becomes the OH group. And then the oxygen of the alcohol becomes the alkoxy group. Okay, go ahead and put an angle there. Don't make it straight. So I said something very important that will help us with synthesis later on, is that the alkoxy group comes from the alcohol. Man, spelling. Okay, start all over. That the alkoxy group comes from the alcohol. The oxygen of the hydroxyl group used to be the oxygen part of the carbonyl group. I mentioned this because what if you want to go backwards? We're going to learn hydrolysis, maybe not in this video, but in the next video, but you can predict now what alcohol and what aldehyde or ketone made these two hemiacetals. The last thing I want to mention before we look at actually, we're not going to look at the mechanism for this. We're going to look at the mechanism of the acetal because it goes through the hemiacetal. So we'll kill two birds with one stone by doing the mechanism of just the acetal formation. But before I get to the acetal formation, I just want to mention that some textbooks, some professors will call this a ketal. And you can think of it as a hemiacetal, oh, not a ketal, a hemiacetal. And that just comes from the fact that this hemiacetal came from a ketone. I don't normally subscribe to that. I'm going to say whether you start from an aldehyde or a ketone, you're making the hemiacetal. I think right now that's still acceptable, and that's how I was taught. I would learn ketal and hemiacetal much later after graduation. Okay, I consider both of these hemiacetals. What is an acetal though? Okay, an acetal is going to be a molecule where we have two alkoxy groups instead of one alkoxy, one hydroxyl. So you can imagine that we take an aldehyde and we go to the half acetal or the hemiacetal, and to get to the full acetal or just plain acetal, we're going to put in another alkoxy group in replacement of this hydroxyl group. Let me write that out, and this is going to be reaction F. Reaction F, acetal formation. And yes, we will be going through the hemiacetal to get to the acetal. An acetal is a carbon, is a molecule with a carbon that has two OR groups. Now, those OR groups could be identical or they could be different. Okay? And then the other two bonds are either to carbon or hydrogen. Okay, two alkoxy groups. Now, there are a couple ways to get to the acetal. We can take a hemiacetal, right, and add another alcohol to replace this hydroxyl group. Or we could say that we start out with excess alcohol from the very start. Let's take the aldehyde that we saw in the previous example. And instead of saying one equivalent of methanol, we're going to say just methanol in sulfuric acid. Okay. For my class, I want students to assume that you have excess reagent to do the reaction as many times as possible. And if I do want you to only react it once, okay, I will put one equivalent over here. Bottom line is we're going to bypass the hemiacetal and only draw the acetal because we're going to add methanol twice now to the dot. How does that look like? Here's your dot, and here is your first alkoxy group, OCH3. And then instead of an OH like we had for the hemiacetal, we put in a second OR group, and they happen to be identical. So now we have two methoxy groups. I'm not worried about how to name these molecules. Just understand that both of these methoxy groups came from the alcohol. A common theme. The alkoxy group comes from the alcohol. Now, if you want two different R groups, you're going to have to make the hemiacetal. And to make the hemiacetal in good yield, you want to only add one equivalent of alcohol. What alcohol do I want to use? Let's use butanol, 1-butanol HCl. Okay, because it's one equivalent, you're only going to add it once, and we have as the intermediate this molecule here, O, 1, 2, 3, 4. Okay, and let's say we want to add another alkoxy group to make the acetal. Right, this is a hemiacetal. Well, we could should we try? I'm trying to think if tert-butyl alcohol is going to be too crowded to do this. Yeah, that seems a little bit tricky. Let's use this alcohol here. That one. Okay, so just follow the pattern. We have to make an acetal. We already have one alkoxy group to the right. And then we're going to replace this hydroxyl group with this alkoxy group. We have an O. That O is connected to, obviously, a carbon. But that carbon is connected to a methyl on the right and an ethyl on the left. It doesn't matter right or left. Just make sure you have those 4 carbons. That is an acetal. Both of these two molecules that I'm pointing at satisfy the general structure of an acetal. Okay, on to the mechanism. Just remember our foreshadowing. Our foreshadowing is that a cyclic glucose occurs through a hemiacetal reaction. Let's look at that cyclic glucose. Can you tell which carbon is the carbon in the middle of that hemiacetal functional group, I guess? Is there a carbon in this cyclic molecule that is attached to a hydroxyl group and an alkoxy group? See, it's not this one, right? This one only has a hydroxyl group. It's not this one, right? It has an OR group, but it's not connected to an OH. It's this one. Do you see how this carbon is connected to a hydroxyl group? And, did not mean to do that. Hydroxyl group, and that carbon is connected to an OR group, an O with the rest of the molecule. There's your hemiacetal link. What about the acetal? Okay, so there's your hemiacetal, and we applied it to cyclic glucose. What about this linkage between 2 rings? Is it really an acetal linkage? Is it really a linkage that looks like that, or looks like that? Let's take a look at lactose again. Do you see how, do you know which carbon I'm looking at? Right there. Do you see how this carbon is connected to an OR and also a second OR? Okay, I know everything's cyclic, but it doesn't change the fact that this carbon is connected to 2 alkoxy groups and no hydroxyl groups. So there's your acetal linkage. Yes, we do have, if those with eagle eyes, we do have a hemiacetal linkage right here. That just means it's ready to make an acetal linkage to a 3rd monosaccharide on the right. All right, enough about that. We will definitely see some of that in, or maybe a lot of that in Unit 3. Let me go through the mechanism, because this is the mechanism that biology uses to make these cyclic glucose molecules, to make these disaccharides like lactose. Let us take this example here, and we're going to go all the way to the acetal. It is lengthy because there are going to be a lot of proton transfers. Maybe after drawing the mechanism, we could come up with some tricks to memorize the steps of the mechanism. Let me just make sure this is focused. Sorry about that. And focus. It changes. Let's go with that. Okay. Methanol and sulfuric acid. We could use sulfuric acid as the protonating source, or we could use hydronium, because you've heard me say that it's always sold with water. Or there is a such thing, I looked it up, as methanolic sulfuric acid. In that case, really your protonating source is going to be methanol that's been protonated itself by sulfuric acid. Don't forget, we're working with excess, so it doesn't matter if we use one of the methanol molecules to be the proton source, like this. We're going to protonate, and I'm going to use, maybe for the first time in these videos, equilibrium arrows, because definitely acetal formation and hemiacetal formation are reversible. Plus, oh, this is good, because I made methanol in this previous reaction, I'm going to use it now. You're protonating the oxygen to make it actually a better nucleophile, to make the carbon a better nucleophile, to attract the methanol. Okay. If we have time, I'll explain why, but I like to think of it as you activated the carbonyl group. Let's describe it as that. Activated carbonyl for attack. By how? By protonating it. And here we have this molecule here. Already, great. Already we have the hydroxyl group. And now we have also the beginnings of the alkoxy group. I say beginnings because we're not quite done, because we have to rip off that hydrogen. We're going to rip off that hydrogen with methanol. Okay, we're protonating that methanol again. And okay, we could cross lines, not a big deal. Look what we made in 1, 2, 3 steps. I hope we made it in 3 steps. OH and our alkoxy group. In 1, 2, 3 steps, we made the hemiacetal already. We're halfway there to the acetal. We did make acid, or protonated methanol, and I think it's going to be useful in the next step, because, let me double check, we're going to protonate, we got to kick out this hydroxyl group, because the OCH3, the second one, came from the alcohol. Both of these O's are coming from the alcohol. Neither of these oxygens are from the carbonyl oxygen. This will take practice. There's no shortcut to learning a mechanism that is this long, but also that has so many proton transfers. And like, why is it necessary to protonate this OH? If I'm thinking that I need to kick it out, OH is a bad leaving group. Okay, so I want to kick out that water molecule now. We did create methanol, and I don't think we're going to use it in this step, but we have to draw it because it was made in the preceding step. What are we going to draw in this step? This is the step 1, 2, 3, 4. The fifth step is the tricky step. Okay, that's how my students always remember it, because we're going to kick out the water by using what I like to call an internal lone pair, a lone pair that is on the molecule already. It's going to look strange, but you got to draw exactly what the arrows are telling you to draw. It's really telling you to draw a double bond between the carbon and that oxygen, and that oxygen is still connected to a methyl group, and we have this H. You did kick out water. Okay. Do you see how those two mechanism arrows lead to this product? Next, we got to get that second alkoxy group onto the carbon, and we're going to do that by now reacting with methanol. The danger at this fifth step is that it's very tempting to use this methanol to come in and kick out water, but mechanistic studies done in the lab say that that doesn't happen. What's more likely to happen, what happens in the vast majority of cases, is that the water is kicked out by making this double bond right here. All right. So can you see how you're going to use methanol to attack and then kick this up? We're almost done, because we do now have back the OCH3. We have that H still, but this methanol, right, this still has the hydrogen. And last step, water. I'm not too hung up about when people use equilibrium arrows and when people use just a regular forward arrow. I did mention that for proton transfers, I do prefer equilibrium arrows, especially for a long mechanism like this. If you draw this last deprotonation, I think we have our product. Okay, how many steps was that? Okay, let's zoom out. That was 7 steps, I believe. 1, 2, 3 steps. 3 steps to the hemiacetal. 4. 5th step, super tricky because we're using an internal lone pair to kick out. 6, and then 7. The strategy or the trick to learning long mechanisms is memorize the first step, okay? And hopefully when you memorize the first step and you can draw the product, which is just following your arrows, then you could say, well, how do I get closer to the product? At this point, you say, well, I activated this carbonyl for the purpose of putting in that first alkoxy group. The rest is proton transfers to eventually get to the hemiacetal. And then our next task is to get rid of this OH group, right, to add the second alkoxy group. The thing is, if you can memorize that first step, I think the first step is where people lose a lot of time and they say, well, man, how do I start? Or what is that first step? Protonate the carbonyl when you're making an acetal. Okay? And then hopefully that's enough of a hint when you see the product to what to do next. And it will build upon itself, right? You will get hints by the product of the preceding reaction. A total of 7 steps. Yes, if you do the backwards version, it will be 7 steps from the acetal to the starter material. Okay, it's just backwards. We're not going to go through that in this video. I'm not sure if I'm going to go through the mechanism, though, of hydrolysis at all. I haven't decided just yet. For me and my class, this is what's important, because it kills 2 birds with 1 stone. How to make the hemiacetal and how to make the full acetal, or just the plain acetal.